Good afternoon, everyone. Welcome back to another lecture on mathematical statistics. I hope you're doing well. So this lecture is preparation for material that you will see after your second midterm, which will be posted in 2 days. So now we introduce the notion of covariance and correlation, which are two of the most simple and yet widely used concepts to measure the notion of dependence between random variables. So as you will see in, say, ST422, the covariance and the correlation is used almost a lot of time. So the definition goes as follows. Suppose we have two random variables, x1 and x2, where we let mu1 be the mean for x1 and mu2 be the mean for x2. Then the notion of the covariance between the random variable x1 and x2 is defined simply as the expected value of x1 minus its mean times x2 minus its mean. And you can simplify via the rule of linearity of expectation that this is the same as the expected value of x1, x2, the expected value of the product minus the product of expected value. So expected value of the product minus the product of expected value. So this here is the definition of the covariance. And the correlation is simply the covariance divided by the standard deviation for x1 times the standard deviation for x2. And so using the fact that the standard deviation or the variance itself can be written as the expected value of x minus its mean squared, we have a maybe more clear or simpler expression for the correlation as follows. So as we will see later in this lecture slide, is that the covariance can be unbounded, and possibly negative and positive, but the correlation lies in the interval -1 to 1. So the correlation is bounded, and we will clarify this in a few moments. So we first note some very simple properties of covariance. If I have the covariance between x1 and itself, that is nothing more than the variance of x1. Indeed, by definition, covariance x1 is nothing more than the expected value of x1 minus mu times x1 minus mu itself, which is by definition the variance of x1. Just to put the index mu1 here. The second and quite useful property is that covariance is also additive. So you have two random variables, let's say 3, x1, x2, x3. Then the covariance between x1 plus x2 and x3 itself, as we say by the definition, the expected value of the product minus the product of expected value. The expected value of x1 plus x2 is nothing more than mu1 plus mu2. And so by linearity of expectation, you can move this as expected value of x1, x3 plus expected value of x2, x3. And then by splitting this out simply for mu1, mu3, and mu2, mu3, you can simplify this out to be the summation of the covariance. So using this fact, we can easily say by 1 and 2 that the variance of x1 plus x2 can be written as the covariance of x1 plus x2 times x1 plus x2, and you can expand this out to be simply covariance of x1 plus 2 times covariance of x1 x2 plus covariance of x2 by linearity of covariance here, where we have used fact 2 by linearity, and so you have this simple expression here. And one quite useful observation and what is usually abused a lot of time, is that if x1 and x2 are independent, then the covariance is going to be equal to 0. And that is because by independence, expected value of x1, x2 is the same as expected value of x1 times expected value of x2 itself. And so by the definition of covariance as the expectation of the product minus the product of expectation, it will have to be equal to 0. Therefore, variance of x1 plus x2 will be equal to variance of x1 plus variance of x2 whenever x1 and x2 are independent. And we have seen this earlier in, say, chapter 3, or in the lecture slide for chapter 3. So you have seen observation 4 earlier. So let's see a quick example. Suppose you have x and y, jointly continuous. So you have a joint PDF of this form. fxy is 2 whenever xy is positive and the sum less than or equal to 1. So we draw this to be simply something along this line. So x plus y lies on under this triangle here. And so therefore, the expected value of x, you can easily evaluate it out to be written in the definition. And because fxy is only defined inside the triangle, we can then change the index of integration carefully. So x goes from 0 to 1. Y plus x is less than or equal to 1. So y goes from 0 to 1 minus x. And so this integration will give you 1 over 3. And then expected value of x squared is computed similarly. Once again, you have going from 0 to 1 for x and 0 to 1 minus x for y. And then the function is now 2 times x squared, and the PDF is 2. And so you can get 1 over 6. And finally, similarly for expected value of xy, similar limits of integration, and answer is 1 over 12. So you can now easily compute the variance and the covariance. So this example here illustrates that technically speaking, there is nothing too complicated about the notion of the covariance, except that the calculations may be quite a bit tedious, because first you have to compute the expected value of x, then you have to compute the expected value of x squared, then you have to compute similarly expected value of y, and then expected value of y squared. Both of these will give you variance of y. And then finally, you have to compute expected value of xy. So to compute the covariance, you may need, say, only say like 3 calculations. But to compute the correlation, you may need to have 5 calculations, which could be quite tedious and boring. But in any case, in this case, we see that the covariance between x and y is minus 1 over 36, and the correlation is minus 1/2. So now we come to show the previous claim, is that the correlation between 2 random variables is always bounded between minus 1 and 1. And this is a simple consequence of what is known as the Cauchy-Schwarz-Bunyakovsky inequality. And you can take a look at problem 5.167 of your textbook for another proof of this result. But in any case, the Cauchy-Schwarz inequality says that the expected value of x1 times x2 in absolute value is less than the square root of the product of the expected value square. The expected value of x1 square, expected value of x2 square. And there are many proofs of the Cauchy-Schwarz inequality. In fact, the Cauchy-Schwarz inequality is one of the most widely used inequality in mathematics also. It's a little bit more elementary than the chain sign inequality for complex functions, but it turns out to be equally as useful and important. So our proof is quite elementary in nature. So let's start as follows. Let t be any arbitrary number. And we considered this function x1 minus t x2 squared. Then by linearity of expectation, we have x1 minus t x2 squared. By expanding the square, it's just x1 squared minus 2t x1 x2 and then plus t squared x2 squared. But because t is a constant, we can move it outside of the expectation. So we have expected value x1 squared, linearity, minus 2t expected value x1 x2 plus t squared expected value x2 squared. Because this is a non-negative quantity, so its expected value is obviously always bigger than or equal to 0 by definition of the notion of the expected value. So we have that this function here as a function of t is always non-negative. Like we said, ft as a function of t is always non-negative. So we can try to find its minimum value as a function of t. So in that case, all we have to do is take the derivative. So f prime of t is simply, the first is a constant, so that's 0. The second one has t, so we have minus 2 expected value of x1, x2. And then the third is plus 2t expected value of x2 squared. And we want to set this to be equal to 0, which is the equation here. In which case, we can get t star, the minimizer, the minimum of ft. T star will be given by this expression here. And so if we have this value of t star, and we substitute it back into ft, evaluated at t star, then after some simple algebraic manipulation, we will get this as a value of ft star. But because we know that ft star or ft is always non-negative, so ft star is always bigger than or equal to 0, and so some simplification will give you this inequality. And this inequality here is obtained by taking the square root of both sides of this inequality here. And so that proves us the Cauchy-Schwarz inequality. So like I said, the Cauchy-Schwarz inequality is very useful, and as we see, its proof is quite elementary. So because the correlation between x1 and x2 is defined in terms of this expression, so by taking x to the 1 to be the centered version of x1 minus its mean, and x to the 2 to be the centered version of x2 minus its mean, then we can say that the absolute value of the correlation is nothing more than the numerator is now x to the 1, x to the 2 for this numerator, and the denominator is x1 minus mu1 squared, it's just x to the 1 squared, x2 minus mu2 squared is x to the 2 squared. So therefore, by the Cauchy-Schwarz inequality, it has to be less than or equal to 1. And finally, we say that in the notion of the Cauchy-Schwarz inequality, equality holds. That means the expected value of x1, x2 is equal to the square root of the expected value of x1 squared, x2 squared. Equality holds only if this quantity is really equal to 0. If that's the case, then the expected value of a squared quantity is 0 if and only if x1 is equal to t squared x2 everywhere. So in that case, the correlation between two random variables is equal to 1 if and only if there exists a constancy such that x1 is a constant times x2. So this is a very useful observation to note. So in summary, what that indicates is that correlation is a measure of linear dependence between two random variables. So what that meant is that if the correlation between two random variables is equal to 1, then that means that x1 is a constant multiple of x2 for some constant. See, if the correlation is equal to -1, then x1 is a constant multiple of x2, but now for some constant less than 0. So in the first case, correlation x1, x2 equal to 1, that indicates something like this. We can think of the relationship between x1 and x2 as being given by an increasing line. And in the case when the correlation is -1, the figure will look more something like this, where this is x1 and this is x2. And now this is some negative function. x1 equal to cx2 for c less than 0. This is x1 equal to cx2 for c bigger than 0. So in the first case, it's a linear increasing, and the second case is a linear decreasing. If f1 and x2 are independent, that implies the correlation is 0. So the converse of that statement says that if the correlation is 0, that suggests that possibly x1 and x2 are possibly independent, but not always. So in fact, example 5.24 in your textbook give an example where the correlation is 0, but x1 and x2 are not independent. So if they're independent, correlation is 0. If correlation is 0, that does not necessarily imply that they have to be independent. So the key word here is that correlation is a notion of linear dependence. So what does that mean? Let us give a quick example. Suppose I have a random variable theta that is uniform on, say, the angle 0 to 2 pi, and then I define x to be cos of theta and y to be sine of theta. So what that meant is that you can think of x and y here as being uniformly distributed on the sphere, on the circle. So this is x and this is y, and x and y lives on this circle where x squared plus y squared is equal to 1. Then you can easily show that the expected value of xy is equal to 0, and expected value of x and expected value of y is also going to be 0. So in this case, correlation of x and y is going to be 0. But obviously, x and y are dependent. But their dependence is not linear. Non-linear, because they live on the circle. So in that sense, correlation is a measure of linear dependence. And in general, say, layman term, people usually confuse correlation with a more general notion of dependence. Correlation only measures linear dependence. Two random variables that have correlation 0 could still be dependent, and usually they will have a dependent structure that is highly nonlinear. So we said two random variables are uncorrelated if the correlation is 0, and if they are uncorrelated, then the covariance xy is also going to be 0, and that indicates that the variance of the sum is the sum of their variance. So if two random variables are uncorrelated, then the variance of the sum is the sum of the variance. And so this holds more generally than independence. So you do not need independence in order for the sum of the variance, in order for the variance of the sum to be the sum of the variance. Okay, so now we're going to move on to another quite useful technique, which is the notion of the variance of linear combinations of random variables. So as we see earlier, we usually, for a random variable, we usually care about its mean and its variance. And we see Chebyshev inequality, which are quite useful when you just need to know the mean and the variance. Another thing that is quite nice is that in many times, the variance of a random variable, a complicated variance, usually can be computed quite simply. So variance also lends itself to easy calculation. So that's why, like I said, a simple and very useful result for the variance of a linear combination of random variables. And see theorem 5.12 in your textbook for more info. So more specifically, suppose I have x1, x2 up to xm. They are random variables, either discrete or continuous or mixed. I don't care. Let a1 up to am be fixed constants. And now I define u to be a linear combination of the xi's. Then the variance of the u, which is the variance of this linear combination, can be written in this simple form here, where we sum up the variance of the xi, weighted by the coefficient ai squared, and we sum over the cross term of the covariance between xi and xj, weighted by the cross term weight ai and hj. So in the case when the xi are pairwise uncorrelated, so what would mean is that expected value of say covariance of xi, xj is 0 whenever I not equal to j. Then that implies that the variance of this linear combination is a linear combination of the variance. So the variance of the linear combination u, linear combination, is now the sum of the variance of the xi weighted by the coefficient square. And this result is quite elementary to prove. So we will skip the proof, but you can see the lecture notes for more detail. But more specifically, all we're saying is that the variance of u is the covariance of u and u itself. That's a typo here, so we delete it. And the covariance of u we can write as a linear combination using the index I, and u here is now written as another linear combination of the index j. And now by linearity of the covariance, what we meant is that covariance of x1 plus x2 and x3 is the same as covariance of x1, x3 plus covariance of x2, x3. Then by linearity of covariance, you can split this into the sum of the covariance. And then some simpler algebraic manipulations give you the final quantity as we claim here. So please take a look at the slides or your book for the proof, but it should be quite straightforward. So similar arguments also show that instead of the variance, if you just have u, which is a linear combination of some random variable xi, and v, which is a linear combination of some other random variables y, then the covariance between u and v once again have the simple form of written as the summation over I and summation over j of the covariance between the xi and yj. So the cross covariance weighted by the weight ai times bj. So as a quick example of this result, and we will use this calculation many times later in this class, and if not, also in 422. So like I said, very elementary result, but turned out to be quite useful. So earlier, we note that if x is a hypergeometric random variable, that its variance is of this a little bit messy expression here, where you have n and r and n, but it looks like the variance of a binomial n times r over capital N, but with a correction term of the form n minus n divided by n minus 1 for the sampling without replacement. So this we saw in chapter 3. So we now rederive this result, but now by writing x as a linear combination of indicator random variables and applying this result here. So let me just clear this out so we can see more clearly here. So clear page. Yep. Where we will now apply this result here. Okay. So with that said, we have let's write x as a sum of indicator random variable I1 plus I2 up to In, where the ij are indicator random variable such that ij is equal to 1 if the jth row result in one of the r possible success event for sampling without replacement. So we therefore have, by the previous result that we saw about the variance of a linear combination, that can be, in this case, ai is equal to 1 for all I. So the first part is just the sum of the variance, and the second part is now the sum of the cross covariance. So because the I are indicator random variable, their variance is easy to calculate. The expected value of expected II of the ith event, indicator random variable, that is simply R over capital N, because there are R success out of N trials, even though the sampling is without replacement. But that doesn't matter. So it's just a Bernoulli trial, so the expected value is R over N, and the variance is by the Bernoulli is just P 1 minus P plus R over N times 1 minus R over capital N. And you can simplify it out to be this quantity. So the next part is the expected value of II times Ij. Because as you remember, the covariance between I and Ij is the expected value of Ij minus the product of the expected value. We already have this earlier, so we just need to find this. So expected value of II times Ij is what? You can think of this here is equal to 1. So II and Ij is equal to 1 if the ith trial and the jth trial are both success. So in that case, the ith trial is a success. You have R out of N possibility, and now you have removed away one success, so you have R minus 1 for the jth trial, and because you have do sampling without replacement, you're dividing by N minus 1. So you have this expression for the expected value of II and Ij, and so the covariance by the definition here simplifies out to be this expression here. And so the variance expression is once again nothing more than some simple algebraic manipulation. So this is the variance of II, which is this term here. And because there are n trials, you sum over I, there's n of them, so you multiply by n. And similarly, for I not equal to j, you have n times n minus 1. Because that's the number of pairs, n times n minus 1, pairs for which I is not equal to j. And some simple algebraic manipulation give you the formula as we want. So like I said, this is nice to know because in many settings, you could write your random variable x as simpler combinations of simpler random variables, as combinations of simpler random variables. So we never have to work with something too complicated. So as another important example of the previous result for the variance of a linear combination, we will see this many times in ST422. So it's good to note it now. So you have random variable x1, x2 up to xn. They're independent and they have the same distribution. So that's what we meant by identically distributed. They come from the same distribution. So for example, they're all standard normal, or say they are all exponential with the same mean, so on and so forth. So if we denote by expected value of xi to be the mu, and the variance of each of the xi is identically sigma squared, and now I look at x bar, which is the sample mean. So x bar is the sample mean of the xi. As we say here. Then we can show easily that the variance of x bar, because it's a variance of a linear combination, and these linear combinations are independent, so you can simplify it out to be the weight is 1 over n, so you move it out to be 1 over n squared, and you sum over the variance. The covariance term is always going to be 0 because they are independent, and so you can simplify it out to be sigma squared over n. So the variance of x bar goes 0 as n increases. The more samples you have, the smaller the variance of the sample mean. Because the expected value of the sample mean is easily shown to be the same as the true mean, Chebyshev inequality says this. And so as we see, for any fixed k, as n goes to infinity, this will always be true. And so you can then let k goes to infinity slowly, in which case you will have a probability that goes to 0 as k increases. So in summary, for any fixed epsilon bigger than 0, the probability that the sample mean is bigger than the true population mean by at least epsilon, that probability goes to 0 as you have more and more sample. So in summary, the sample mean is a consistent estimate of the population parameter mean, mu. In fact, this is not the only case. There are many other cases. This is a simple generalization of this one. So you could replace the sample mean of this xi to be some other function of the xi. For example, we can think about some random variable such as g of x1 and say the g of say the xn, in which case we can show that the sample mean of the x bar, so 1 over n, summation of the g of the xi, will converge to the true mean will go to 0 as n goes to infinity, as long as the expected value of, as long as the variance of gx exists. And so as long as gx here, so as long as gx is measuring some important quantity, we can always estimate. So as long as the expected value of gx is measuring some important quantity, we can always estimate it consistently. So we present the result here from the sample mean, but it is true in much more general details. So for that, you will have to wait until ST422. So now we will move on to the notion of the multinomial distribution. So this is one of the most famous multivariate discrete distribution. So as you will see in chapter 5, we talk about multivariate distribution, but we do not talk about any kind of like exemplary kind of distribution. In the discrete case, univariate, we have the Poisson, we have the binomial, we have the hypergeometric, we have the negative binomial, so on and so forth. But for the multivariate discrete case, we seem to be talking about just very, say, like specialized examples. And the answer is just because there is not a lot of classical and widely applicable multivariate discrete distribution. One of the few exceptions to that is the multinomial. which is very commonly seen and very widely used. So the multinomial distribution is nothing more than the generalization of the binomial to more than three or more outcomes. So the binomial experiment we might want to recall in chapter 3, but the multinomial experiment is similar, and it's basically an experiment in which you consist of n trials that are all identical, where n, the number of trials, is assumed to be known a priori. So this is similar to the binomial. Now, instead of resulting in only two outcomes, success or failure, each trial now results in exactly one out of k possible different outcomes. So you might think of these possible different outcomes as maybe like red, green, blue, or success, failure, indeterminate, or those kind of things. But each trial results in exactly one out of k, capital K, possible different outcomes. And these trials are also independent, similar to the binomial case. Now the probability that the ith trial result in the kth outcome, little k, out of the capital K, is pk. So the main emphasis of the pk does not change with the trial I, and the sum is equal to 1. So like we said, in the binomial, capital K equal to 2. So it's either p or 1 minus p. For the failure, in this case, we have more than two trials, possibly. Two outcomes, possibly. So in just to be obvious, so k equal to 2 leads you to binomial, and k equal to 3 leads you to the general multinomial, or what we call as the trinomial, and so on and so forth. So associated to multinomial experiment is a multivariate random variable x, which is x1, x2 up to x capital K, where x for little k is the number of trials out of the n trials, and out of n total trials, for which the little k outcome appears. And so the sum of all these little xk from 1 up to capital K has to be equal to n, the total number of trials. So in that case, we say that capital X is a multinomial random variable with n trials and capital K outcome. And if we are given the vector P of probabilities of each of the capital K outcomes, then by definition, or by, I guess you could say the definition, or more like proof, whatever you want to think of it, but definition is good enough, then X has a joint probability mass function, where the probability mass function that capital X1 is equal to little x1, capital X2 equal to little x2, up to capital Xk equal to little xk, is given by the multinomial coefficient that we saw in, say, chapter 2. Because we require that x1 plus x2 plus plus x capital K have to be equal to n, so that's the multinomial coefficient, multiplied by the probability p1 times x1, p1 to the power of x1, p2 to the power of x2, all the way up to p capital K to the power of x capital K. So there's a small typo here. So that in itself defined the notion of the multinomial random variable. So as we see, there is the multinomial coefficient, and then there is the associated probabilities that x1 trials resulted in outcome p1, and capital Xk trials resulted in the capital K outcome. So just another simple comparison. In the case of the binomial, you have the binomial coefficient. That's all. And finally, we just want to emphasize that P capital K is nothing more than 1 minus P1 minus P2 minus dot dot minus P capital K minus 1, just to be obvious. So this example here is from the lecture note by Dr. Tabbs over at University of Southern Carolina. So the example says that the state laboratory tests thousands of residents each year for some kind of, I guess, STD disease. So on a given day, suppose that the lab received 1,000 trials specimens, and that the probability of each specimen go into category 1 is 0.9, into category 2 is 0.07, and so on and so forth. So P is 0.9, 0.07, 0.02, and 0.01. That K equal to 4 outcomes. Then if we care about the multinomial random variable, denoting the category counts observed after this n equal to 100 trials for testing, then we can say that capital Y is multinomial with 100 trials and this probability vector capital P. And so if you're interested in the fact that you have 88 specimens in category 1, 10 in category 2, and 3 and 4 each have a single category or single specimen, then by the definition of the PMF, the joint PMF for the multinomial, that expression is given below. So we will see the multinomial distribution quite more often in, say, chapter 10 or 11 of ST422. So we'll come back to this topic, or you will come back to this topic later. But another quite well-known use of the multinomial is as a case of conditioning on the sum of a Poisson. So if you have x1, x2 of the x capital K, and they're independent Poisson random variables, and they each have different rate parameters, lambda 1, lambda 2 up to lambda capital K. And now you let S be the sum of this Poisson. So then what is the distribution of the multivariate random variable x1 to x capital K given the value of this sum? So you can think of, for example, like x1 up to k denoting the number of customers coming into, say, store 1, store 2 up to store capital K of, say, a certain franchise. Let's say Cookout. So now suppose you already know the total number of customers that comes to all the stores at a single day. And so you want to say, given that, say, 1,000 customers come to all the stores, how many of them come to each individual store? And the answer turns out to be given by the multinomial distribution. And the proof is quite simple. Suppose the total sum is n. There are in total n people visiting all these K, capital K stores. Now you let lambda be the sum of the rate parameter. Then we know that S is Poisson with rate parameter lambda. Thus by the property infinite divisible of Poisson random variable. So therefore the joint PMF of X given the sum, you can say that given S is equal to n, that is this quantity down here, so that's the property that S is equal to n. And this is the probability that x1 is equal to x1 up to x capital K is equal to x capital K, and that S is equal to n. So this is only true in the case when x1 plus x2 plus dot 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 plus x capital K is equal to n. In that case, because they are independent, this is probably x1 is equal to little x1 is simply this first term, x2 equal to little x2, that is this second term, xk equal to little xk, that is this term. And then after some simplification, you have n factorial here, so you move it up to the numerator because you divide it in the denominator, and then you have this x1 factorial, x2 factorial, and all the way up to xk capital factorial. And then the remaining part is simply shown to be as follows. And this is nothing more than the PMF of a multinomial, where now the outcome properties is now lambda 1 divided by the sum, lambda 2 divided by the sum, and lambda capital K divided by the sum, lambda. So we have a very, I think, elegant result. In simple words, if you have a bunch of Poisson and you condition on the sum, then the joint distribution of these Poisson conditioned on the sum is multinomial. So, because this is a multivariate random variable, we could then talk about its covariance and correlation. So if we have a multivariate, a multinomial with outcome properties P given by as follows, then the mean for each of the xk is n times pk, and the variance is n times pk 1 minus pk. So one will emphasize is that xk is marginally the same as binomial and little pk. And that's just because you can think of the remaining categories, capital K minus 1 categories, to be grouped into a single category, failure. Okay? As long as it's not the little k, then we view it as failure. So the mean and the variance for each marginal is well known. And finally, between any two category, capital K, capital L, or little k, little l, their covariance is minus npk times pl. So the covariance is negative. So that means that the correlation is negative. And that suggests that, yes, that if xk is large, then xl is likely to be small, just because the sum has to be equal to n. So if one value is larger, the other value have to be smaller. So the proof is, like I said, quite elementary. The expected value of the variance follows directly from the binomial. So we can now derive the formula for the covariance. And the formula for the covariance, once again, use the linear combination of indicator. So now for the kth outcome, we can think of it as a sum of indicator random variable, where I, little I, k, is the indicator random variable that is equal to 1 if the ith trial result in the kth outcome, at 0 otherwise. So it's the indicator that says at the ith trial is my outcome k. If yes, that's 1. If my ith outcome is not k, or if my outcome is not k, then that will be 0. So once again, the covariance of a linear combination can now be written as the sum of I and j of the covariance pairwise between the kth, the ith, and the jth combinations, or indicator random variable. I emphasize here the importance that IIK has a different trial than possibly IJL in the case when k not equal to L. So now we can same simple straightforward calculation. The expected value of IIK is pk because this is nothing more than Bernoulli with success probability little pk. Now if you have the same trial, ith, but different category, then the expected value of the product has to be 0, because you cannot have for the ith trial both category K and category L if they're not the same category. So their expected value of IIK, IL is always going to be 0. And if they're different trials, then they're independent, because the multinomial says that you have a sequence of independent trials. So you can write it as the expected value of the product of the expected value. So easily we see that in the case when the trials are different, the covariance is always going to be 0 due to the independence. And in the case when they are the same, then when you have the same trial, then because of this result here, the expected value of IIK, IIL, which is always 0, minus the expected value of IIK multiplied by the expected value of IIL. So this is 0, and then this is simply PK and PL. So we have minus PK, PL here. And so with that said, by the rule of the linear combination, you will never care about the sum over I, sum over J, I not equal to J, of covariance IIK, IJL, which is 0. So we just have the sum over I itself. And that is simply minus NPKPL as we claim. So in summary, once again, we see that the result for the variance of a linear combination turns out to give us quite useful result. It's a simple but powerful result.